first talk will be by Benedikt, Ahrens, and LELAY about the Unimath library.
Thanks a lot. So the goal of this talk is to first explain what Unimath means. In the second part, I will give a quick overview of how to use Unimath in case you feel encouraged to try it out. And the third part will give an overview very briefly over some of the contents of Unimath, the Unimath library. And Katrin will present in more detail some of these packages. So, what is Unimath? First, it's an abbreviation for univalent mathematics. But then by this term Unimath, we mean at least three different things. Firstly, a language for the formalization of mathematics that I will talk about. Secondly, a library of mathematics that is formalized and computer checked in the Unimath language. And thirdly, also a team of people contributing to this Unimath library. The overall goals of the project are as follows. In terms of the language, we want to have a core type theory that is, on the one hand, sufficiently small that we can be confident that it's correct, in the sense that we can give a model of the complete language. But on the other hand, also rich enough to formalize a significant part of mathematics, if not all of mathematics. In terms, our goals for the library are that we want to have a library that is usable by professional mathematicians and that goes beyond, let's say, undergraduate mathematics. In particular, we are not specializing on any particular field of mathematics. You will see that there's a lot of different mathematics in the Unimath library. And, well, in terms of content and form, it should be accessible and usable by professional mathematicians. So, in particular, the fact that we are targeting, like, let's say, average mathematicians as an audience or as a user for Unimath will motivate a few design decisions that I will talk about. So this is let's say, an idealized version of the type theory that we're working in. So we have sigma types, product types, coproduct types, identity types, two universes, and a few base types. In particular, we're using the eta rules for both sigma and pi. And we have two axioms that we're using. Firstly, the univalence axiom, and then stated as a separate axiom, but formally a consequence of the univalence axiom, function extensionality. And importantly, one rule is a version of propositional resizing. Here I just say, if it's locally any proposition lives in U0, there are variants of this resizing rule that one can think about. For the time being, it's just this rather sloppy formulation of the resizing rule that I will refer to. So this is a theory, but in practice, we don't have a proof system that implements exactly that language. So what we are doing is we use the Koch theorem prover and adapt it to our needs. What this means in practice is that we restrict ourselves to a subset of the Koch language. So in particular, we don't use record types, no general record types, I should say, no inductive types, and no match construct. So if I go back to the theory language, then of course my sigma types, coproduct types, identity types, and these types, they are implemented as particular inductive types. But beyond these, we don't use inductive types. Apart from that, there are some Koch features that we rely on to adapt Koch to our needs. In particular, the resizing rule is not formally available in Coq, so we enable that by using the very crude type in type flag, which effectively just deletes universe checking, so we have to keep track of universes by hand. Okay. The identity type would usually be put into Coq's prop universe, the use of which we want to avoid. So this is another flag called indices matter that avoids this universe prop and puts instead the identity type in the same universe as the indexing type. And eta for sums, we've just recently gotten that through the use of primitive projections. So the sigma type is defined as a record type of primitive projections to implement eta for our sums. Okay. Interrupt me anytime you feel like it. Outside the kernel, we are using some of Coq's features, but not all of them. In particular, we make use of coercions, which are particularly handy for everything that is abstract algebra. Implicit arguments are important. We have a lot of Unicode notation and other notation. And we use Coq's tactic language, but we try to restrict ourselves to tactics that are extremely simple. In particular, as you see here, we don't have any proof automation. We try to avoid that. We also avoid canonical structures and type classes. Okay. Good.
So, what is the reason why you want to avoid proof automation?
So the reason for me is that writing down a proof, even if there are many details, it's a kind of documentation. And once I have written down the proof, then I have a trace of that proof. If I rely on Coq to create the proof for me, it might fail in a future version. And then I have no written trace of the proof anymore. The proof is just gone.
Well, I can suggest a very practical reason. Suppose you're giving a talk about your development and somebody asks you how you proved that. You're supposed to be able to answer such a question.
He says that you say auto.
And auto is if you, well, I don't think it would give you high marks.
I mean, decision procedures are not so powerful, so usually it's obvious what's in to prove.
Yeah, well,
annoying to write down.
Yeah, sometimes we're more thinking about creating specific tactics for working with specific, for example, algebraic structures in Unimath, and then we kind of will know that they're doing it. I also want to say that we haven't used canonical structures because our dependent sum was an inductive type, and so we couldn't. It needs to be a record, or at least it used to be necessary for it to be a record, so that canonical structures will be enabled. So now it is a record, and it might be that we'll start using canonical structures because they seem like harmless enough and powerful.
Well, also when you give a talk on Unimath and every feature that you use, you have to explain to a potential user. And since our target audience is maybe technically not so savvy mathematicians, the fewer features we use, the fewer features we have to explain to make the thing usable. So I would advertise against the use of canonical structures.
So you are using records now.
We are using
One record. We're using a record. Dependent sum is defined as a record, or parameterized by two parameters, but the word record is not allowed in the text of the library.
Why no inductive tests?
Because it's a challenge to do without, and we like the challenge. I mean, okay. More seriously, it increases the burden on the mathematical justification of the syntax. And we could restrict ourselves to like a well-understood class of inductive types, the W types. But then these in practice, if you really use them as W types, since they are all functions, they're not very convenient to use anyway. So the convenient version of inductive types to use are Cox native inductive types. But these are not theoretically well delimited, I think. So there's no mathematical theory of Cox inductive types. So we would have some trouble justifying them as math.
Yeah, I mean the basic reason that we don't know how to semantically justify it. First of all, because it's difficult. I mean, I sort of have checked it that it roughly seems to be right semantically some many years ago, but it's difficult to do it precisely, and the exact details seem to be changing from version to version, which makes checking it precisely even more challenging. So we fixed a subset which doesn't change, and for which we know that we only once need to check that it's semantically justified and work with it.
Other questions? Okay. So the library, the Unimath library, in theory, well, it's a library of mathematics written in the Unimath language. And in practice, it amounts to a collection of Coq files which are restricted in the language that they are allowed to use. And in addition, some infrastructure for convenient usage of these Coq files that I will discuss briefly later. So the Unimath library was born by combining three separate libraries. Once the Foundations library written by Vladimir, then a library on category theory, which was called rest completion because this was the main theorem at that time proved in the library, and a library on K-theory. Unimath is available on GitHub. So here I should explain that this Unimath, this usage of the word Unimath refers maybe to the Unimath organization, and this word of this usage refers to this library.
Clearly they're different because one's slightly to the right of the other.
Okay, so the Unimath library is organized in packages. I will give some details on the contents. So we have foundations. We have more foundations, which I will explain why there are so many.
There is a good reason.
Algebra, number system, real number. So what is important is that you see that there is not one field of mathematics that is prioritized over other things. A bit of a bazaar of fields of mathematics in Unimath. It consists of approximately 100,000 lines of code. It takes very long to compile. 13, like I counted only the substantial contributions were made by 13 contributors in total, and it's distributed under a free software license, which is normal nowadays, but still important to mention. Before going, so I said I will go into the details of the contents of the individual packages later together with Katrin. For now, I want to say that there's one more repository of one more library that is based on the Unimath library, and this is why I pointed out what these words refer to. So we have another repository called Unimath type theory, which adheres to the same guiding principles, so it adheres to the same language restrictions as Unimath. Unimath, it hosts some material on categorical structures for type theory, so this is, let's say, this is really some research level mathematics formalized in this library. The reason why we have it in a separate repository is that we want to not be bothered too much by the review process that it's a lengthy process to sometimes to get code into the main repository. And this repository has about 60,000 lines of code at the moment.
What makes the review process so hard or lengthy?
Sorry?
What makes the review process so hard or lengthy?
Well, we have an informal rule that at least 2 people read the code that is supposed to go into Unimath. And for this code that we're writing here, it would be difficult to find 2 people who are not the authors. I mean, 2
Or even one guy?
Well, yeah,
Yeah,
I mean, this is mostly written
I
by
mean,
Peter
there
and
is
me.
3 of us, so technically speaking, there is always
Yes.
2 people, but we all
We are all very busy,
and,
yeah.
and
Okay. So, yeah. Now I will give a few pointers to how to use Unimath and what kind of features are available for the practical usage. Unimath uses Coq as an underlying framework, so to make this kind of invisible or as transparent or as invisible to the user as possible, we have Coq as a submodule of the Unimath repository. So what happens is when you first try to compile Unimath for the first time, Coq will automatically be downloaded and compiled for you.
is it so necessary?
It's not necessary. You can, if you have your own version of Coq already installed, you can deactivate this, but you have to do something to, it's an opt-out rather than an opt-in.
Okay.
The compile time for the whole of Unimath is very long, as I said. So importantly, we can make individual packages which just make all the content of this package plus the dependencies necessary to compile these packages. This PDF here that I will make available, it has links, so if you are really interested in trying it out, you can just open this PDF later and click on the links.
Well, may interrupt for a second. On my computer, it's not terribly long. So I have a MacBook Pro about 2.5 years old or 3, and I mean it's it's boring to sit looking at the screen while it compiles, but if you kind of have a couple of small things to do around, well, maybe it's, I don't know, 15 minutes or.
Well, it depends on if you use parallel compilation or not. So Katrin has a very small computer. It takes.
Yes, I have a small computer and I work on a virtual machine in this computer. Then it is very long to compile everything.
Well, virtual machine is probably makes it.
Yeah, because then it's not parallel, I guess.
So as I said, it depends on a computer.
How exposed are you to future changes in Coq? I guess it doesn't change hugely from version to version.
It doesn't change. I think in the past we started out with Coq 8.3, I think.
Yeah, I think like first version of Foundations. Yeah.
Was Coq 8.3. Now we are at Coq 8.6. So in all these changes, we didn't have a lot of trouble adapting. It's also because we restrict ourselves to this part that doesn't change. Like if we were to use type classes, then it would probably be a total mess every time.
Just to give a comparison as someone who's been involved a bit with both Unimath and the HOT library, the HOT library uses a lot of sophisticated features, and that's nice when you're using them, but then it means it's harder to migrate from different versions to Coq. Unimath has, from what I saw, had a lot less difficulty migrating as Coq goes up.
I think the biggest issue was when we introduced the primitive projections for the sigma times. But that was not tied to a version change. Okay, so if you want to edit the files, our workflow is optimized for usage of Emacs. Quite difficult to get used to, for me at least, but I have mastered, and I think you can do too if you want. There's some infrastructure to make this work smoothly. For instance, if you open a file of Unimath with Emacs, then proof general or Emacs, I don't know which one of these really is responsible, is automatically pointed to the version of Coq that you have compiled for Unimath, even if you have not adapted the path or done whatever thing. We ship the ACTA Unicode input mode as well, so this is automatically loaded when you visit a file, a Unimath file, and there's also this Emacs tags mechanism that is good for file search and replace, for instance, if you type make tags. Coq IDE can be built also if you are inclined to do so, but there is, apart from this command, there's very little support to make Coq IDE, to make it convenient to use Coq IDE to work on the files. We do have two versions of HTML documentation. One is a standard version, and one is like a tiny enhancement that I can maybe demonstrate on this. So, with the possibility to write proofs. Very cool. It's not our idea. It's not our idea, but it's just that we took this code from a few friends and integrated it into Unimath. So I don't know how to do this here, but you could just try it out by yourself. Okay. How to get help? Yeah, we have documentation that is very partial, unfortunately, but for everything that is not explained in the documentation, we have this mailing list where friendly people respond, hopefully. And if, on the other hand, you choose to help in the development of Unimath, then there are a few tasks that are easy to attack. For instance, we have one package that is on periodic numbers, which is in urgent need of an update so that it would compile with Unimath. It's currently, it is part of Unimath, but it's not part of it's not compiled because it doesn't compile. So that's a construction side that would need some attention. Documentation and installation instructions, we are always happy. Like, for instance, we don't have installation instructions for Windows, so if somebody, for whatever reason, works on Windows and wants to contribute installation instructions for Windows, that would be very welcome. And then there are a few in our bug list of bugs. There are a few issues of relatively simple tasks that might be an entry point into Unimath. You can click on this. This is a link. You can click on it, and it will give a list of all those tiny tasks that you might want to attack as a starting point. Okay. So that was on how to use Unimath. I will now start with describing the contents of some of the packages of Unimath very briefly. So the first part is foundations. This maybe is a specification of what we mean by univalent foundations. It's a specification of the theory we work in, and gives then the fundamental definitions of the univalent foundations. In particular here, in this part, we define the type and term constructors we are using. We define weak equivalences and the important notion of homotopy level. And then there's a collection on the particular levels of propositions and sets. Statement of the univalence axiom, consequences such as function extensionality, arithmetic on natural numbers, and some other stuff that I mentioned. There's also this package, more foundations. One reason, but not the only reason for this package is that there's a big difference between mathematically, like the amount of mathematically interesting theorems and the theorems that are necessary or convenient to have for formalization. And this package, more foundations, is to make up for that difference. So for instance, here's a construction that is mathematically interesting, but there are at least 2 variants here, and then you can think of 2 other variants. So there are at least 4 variants of this lemma and of this construction, and all of them are important or can be important for formalization, but only one has mathematical content. So this construction gives an equivalence between equalities of pairs and pairs of equalities. So if we put all of these variants into one file, then reading that file gets extremely annoying and upsetting. So the idea is to have one variant in foundations and putting the other variants in more foundations. And this more foundations is not meant to be read, but rather meant to be searched in some other way. So this is related to Vladimir's idea, which maybe I quote hopefully correctly, of this package foundations as a textbook, say, on univalent foundations, as a specification and as a book that one can actually use to teach univalent foundations.
Yeah, and it's kind of the idea that it is structured in a way in which kind of one author or 2 closely interacting authors may structure a text with a lot of kind of higher level structures in it. And it's basically locked. So if one wants to add something foundational, one adds it into more foundations. Because otherwise, we have kind of arbitrary number of authors. They start inserting things in arbitrary places in this highly structured text and destroy the structure. And so it's, to avoid that, we want to keep it more or less locked, except for the adapting to the new versions of Coq and so on. And all the contributions to go into more foundations, where they can be kind of organized in a more kind of computer sciencey way, the way you organize a program where you don't expect it to be read.
Bit like the exercises in a book. So everything you don't want to elaborate, you put in the exercises.
Something like that, yeah, maybe.
What are the relative sizes?
Hmm?
Relative sizes of foundations and more foundations.
Well, we just made this flip, and there is still some work to be done on kind of cleaning up the foundations.
So this is a plan for the future rather than a current state.
So so far very small more foundations because we had just started to implement
the
the
exercises.
idea.
I have a question on practice. So how do you represent natural numbers?
Natural numbers are one of the inductive types of the native Coq inductive types that we use. So, you know those.
But would you use booleans? Inductive type for booleans?
Yes. So I don't go back to the very first slide, but there were 4 base types that I mentioned: natural numbers, booleans, 1 and 0, and those are all implemented as Coq inductive types.
But you never write recursive functions, you just use the eliminator.
Yeah, we try to
We try to use the eliminator. I mean, kind of creeps in, but the struct creeps into the proofs, and that we.
Okay, there's a package called combinatorics, which defines standard finite sets which are sets that have together with equivalence to a standard finite set, finite sequences, ordered sets, well-ordered sets, and I think then Grayson quite recently proved as a highlight, say, of this package, Zermelo's well-ordering theorem.
Has he actually proved it? I mean, I know that he was somewhere very close when he was distracted by some other.
I looked it up yesterday evening, and there was a thing called Zermelo's well-ordering theorem with this statement. I hope there was no hidden admit.
but anyway, he is close. And just one small correction: finite set is not a set with an equivalence.
So
Is a set for which there exists an equivalence. Exists, we always try to use the word exists in a weak sense, and the word given when we want to say strong exists.
yeah, what I didn't mention is how propositional truncation is. Was that your question? Yeah, is implemented in Unimath. So it's implemented via a predicative encoding. So this is one place where we need this propositional resizing. Okay. Category theory is maybe one of the fastest growing packages in Unimath, simply because there are many people interested in category theory and use category theory then to do other stuff on top. There's categories and univalent categories, and most of this is very standard. So I would say that a large part of the McLean book is covered, or is very close to being covered in this library. And then, in addition, we have this univalent categories and the construction of the rest completion, which is a new aspect of univalent foundation. I think that was my part, and Kathleen will now talk about some other
Can I ask a question?
Sure.
Can you say a little bit more about resizing? I'm interested in that. So what exactly are the resizings that you use in Unimath?
We use, so I think we use the following resizing rule: every proposition automatically lives in the lowest universe. Now, in theory, Vladimir could give a whole talk on possible resizing rules about, like, if a given proposition should always be equivalent to a proposition in the lowest universe, or if it should directly live there.
No, we use strong resizing rules. So the strong propositional resizing rule. So everything which for which you have proved that it's a proposition can be considered an element, directly considered an element of the lowest universe. We also use, I would say that we also use the second, there are just two resizing rules actually. There is this one, and then there is a rule which says that given two universes and two types, one in one and another in another, and an equivalence between the two, their universes can be exchanged.
Right, and the type of propositions itself, is it small or not?
So the type of propositions, then you can prove that it is small using these two rules, because the propositions in two universes turn out to be weakly equivalent to each other. And by the function which takes a proposition to itself. And this is a weak equivalence, so you can apply the second rule to deduce that proposition. The H prop lives in the second universe. So if you have U0, U1, and then U, then H prop of U lives in U1.
So
But all H props live in U1.
Okay, so U1 is the smallest universe that has H prop. You don't have H prop in U0. Or there is
Well, there is an H prop in U0, but you cannot prove that if I remember right, why was it that, right, but you cannot prove that that the U1 prop is the same as U0 prop. I I mean, no, you're right. There is no prop in U0 because the smallest prop you can H prop you can obtain is by taking a sum over propositions in U0, and that will live in U1. So this is the first universe where there is an H prop, and then every other H prop is delegated there because it's equivalent to it.
But can't you have very large very large contractible types?
Well, in the set theoretic model, of course you can. Well, I was going to I'm sorry, Cass. So we resizing rules are mysterious. We do not have their set theoretic justification, and we believe in their consistency just as we believe in the consistency of the ZFs. So that's.
So you can have inductive types as well then.
No, we cannot have something which changes all the time. Resizing rules is something which we control, and the inductive types and book is something which we don't control.
The resizing rules, at least we know what they are, even if we don't know how to model them.
I think we should let Catherine talk about the costs of packages and maybe postpone this discussion.
Okay. Yeah, because it is a long discussion. Right?
I'm sorry, yeah, I guess many interesting things.
You're right.
Now let's talk about the package algebra. As algebras, there is definition of monoids, abelian monoids, ring, and abelian groups. Yeah. For one operator with two operators, we have other structures with only addition and multiplication, and some structure with a multiplicative inverse. And for all these structures, we have many properties and definitions. In particular, to define a group using with a monoid, it means that we would like to add an additive inverse. Then we have abelian group diff, and we have a corresponding notion to transfer for the multiplicative property, and we have to give to him an abelian monoid, a sum monoid, which are the positive numbers, and for both of them, we have the group is defined as a quotient on pairs. And here it is a definition for only one operator, and it is generalized for ring and for field. And these constructors are also used to define integrals using the Ecom ring on natural numbers, and also to define rational numbers. On these different algebraic structures, many properties are proved about orders, relations. There is also the notion of lattice, which is defined, and many theorems about lattice in groups, in monoids are also proved. When we are in a monoid, then I have a general definition for a truncated minus, a general characterization, which is really useful for many proofs. And there is also a definition of the Archimedean property in each of these structure. And there are also proofs of the conservation of properties as compatibility with order when we use the function abelian group diff and harmonic frac, and the generalization for the range and the field.
Catherine, may I just, I don't know if everybody knows what a rig is. Yeah?
Semi-ring? Because it doesn't
You know what a rig is?
Ring without the
It is a semi-ring.
Yeah, without the negation. Without the mind. Turns out to be quite useful for as an intermediate. Bourbaki didn't introduce, but it's actually quite.
It's often also called a semi-ring. It's often also called a semi-ring.
Well, it's actually semi-ring plus some additional axiom because it has an axiom that 0 times x equals 0, which a semi-ring I don't think includes.
Some authors include that in semi-rings.
Huh?
Some authors include that in semi-rings.
But
really short.
Yeah, there are many properties about algebra and
Polynomials?
sorry,
Polynomials?
not yet, but it can be added and proving that polynomials have algebraic properties, then you will have for free many theorems. And in particular for polynomials, you can have you can define formal functions using Bonnet frac. Yeah. And you have many things which can be done for free. And we will see an example with real numbers, because real numbers are first defining a set of non-negative real numbers for which there is a strict and a large order, an apparent solution, an injunction from non-negative rationals to Dedekind cuts, which gives us a 0 and a 1 element. And there are also many functions. And this set is proved to be a lattice, that it is another division rig. It is Archimedean and complete with the definition of Cauchy. All Cauchy sequences are convergent, and also in the Dedekind meanings, which means that if we do the same process on this set of non-negative rings, then we don't add any numbers. We have exactly the same. And we apply the things I presented in algebra, because real numbers are not defined using this general function, which transforms my commutative rate of non-negative real numbers into real numbers. And I have for free the ring properties, order and apartness, the Archimedean property, and also the lattice structure, to prove that it is the set of real numbers. I defined a function which returned to me a pair of Dedekind cuts, and I prove that I have a multiplicative inverse, and that this set is Cauchy complete.
This minus over there is the truncated minus of the non-negative reals, because they have all the structures, lattice structure and ring structure, and then Catherine's general definition of a truncated minus can be used. It's quite cool, actually.
Yeah.
The algebra
and in a future Paul request, I also have a generic function for that. When I already have a truncated minus, then using this pair, I can return a generic function, which is useful because it is the smallest representant, and then we have many properties. Now, as I have real numbers now, it's better if we can do analysis on these numbers. The first thing to define is topology. The topology is based on Bourbaki book, and I first defined the notion of filter, which is a correlation on subsets, and I define many ways to have filters as the creation of neighborhoods of a point, or the image of a filter, and using that I can define the notion of limit, and the usual meaning of the limit is a number x is taking g as locally x. Now, I talked about neighbors, but I still need to define it. Then, topology is defined as the usual way by the creation of open sets, and there are many ways to define the topology. And giving the set of all open sets, or a base of topology, and it rebuilds the sets of all open sets, or product of all of two topology, or using the creation of all neighborhoods, which is really useful because we don't need to describe all the open sets, we just need to describe which is to be the neighborhood of every point in our set, and also other way. And as a notion as topology wasn't enough to formalize things as completeness.
So you do not state that a infinite set of open sets is open.
Sorry?
You do not state that the infinite set of open sets is open.
Infinite union.
The infinite union of open sets. Yeah, I also have this question.
Or is it just
You say topology on X is a collection of O.
There's a typo in the first bullet.
yeah, I guess.
Yes, it is a mistake on my slide because it is in. Sorry. Just a mistake. Sorry, yes. It is an infinite union here and not. And the two other points in the basic definition is said as every finite intersection is also open, but it is easier to prove that if the intersection of zero open set is all the set, then
You also need the empty set. You also need the empty set.
yes,
would
but
follow
it
from
is
arbitrary
included
unions.
in that. The union of zero set is empty set, but
Okay.
yes, I forgot it.
But yeah.
It is just a mistake. Yeah. And I've said it is not enough to formalize useful notions as completeness. For this reason, I formalize uniform structure, which is a filter on pairs of elements with additional properties. And in a uniform structure, we can deduce a topology because taking the projection on points, we have a creation of neighborhoods. And finally, I formalize the notion of Cauchy filter. And a set is uniformly complete if all the Cauchy filters admit a limit, which just means that the the limit of this filter for the ideal function is locally X. Okay. Then there is a set for limits and convergence of theorems. And now
It's yeah. So it's if someone is confused at this point, which I to some extent is it's the second half of the first volume of Birmingham topology.
yeah, all of this part is based on Birmingham.
So now that you mentioned this, are you using non-constructive principles for topology or not yet?
Not yet.
Okay, because topology at some point
Yeah.
requires you to use this.
There's some
Yeah.
If we return on the here in Bourbaki, it is just said the filter do not contain the empty set, but to be constructive, I needed to have this formulation of we don't have the empty set in the filter.
Yeah, but I mean when you start proving the Tikhonov theorem and things like that, because we know it's equivalent to the axiom of choice, so at some point you will need.
well, quite often one simply doesn't need this very nicely looking theorems. And one can replace them by something less nicely looking but constructed.
Yeah, I agree with that. I'm aware of these issues, but the question is whether you want to formalize classical topology or you want to do it in a new way.
Actually, that was supposed to be a very end of my talk on Monday. It's one of the directions where I would like us to move, and I'll talk about it. There is someone who might be interested in formalizing some manifolds theory and most manifolds and the kind of at least some of this new constructions. I mean, like one would, for example, maybe we want to define Gromov-Witten or at least see what is involved in their definitions that we cannot do constructively, or where is, and maybe we want to define them in a univalent way so that they will be automatically invariant under things like equivalences of the appropriate culture. Sorry.
To finish, there are also other packages about folds, homological algebra, K-theory. I talked a little about the number system, but there are more theorems which are specific to integers and rational numbers, substitution systems, and tactics. Thank you for your attention.
Any question?
So if I say, oh, I just want to do classical mathematics, can I do that? Can I sort of just add a little axiom? Is that all? I mean, or
There is a file with decidability on the proposition, and using this file you can do things about classical mathematics, but you have to include it explicitly to use it, and then you know that it is classical.
yeah, good.
So Dan Grayson, his proof of Zermelo's theorem is probably the first non-trivial classical result which we have, and I very much also approve of developing in that direction, because we understand that classical mathematics is kind of a more simple version of constructive mathematics, but sometimes it's very important to have a simplification where you can get a result and then you can think about how to do it in this more complex world of constructive mathematics.
Do the algebraic structures look more or less like they do in Cog, or do the design decisions make them look different?
The algebraic structure, it's a long time I didn't work with, but here it is a sum of a set and the product of all the properties. Then it is similar if we use different projectors, the use is similar and the definitions are also similar.
Any other question?
I was wondering whether the circle you have here, does it live in U1 or does it live in U0? There's this question whether types live in the bottom universe or the highest universe. And
It's in U1.
okay, and for a quotient of a set modulo equivalence relation, if the set is small, then the quotient still lives in U1. Do I understand that right?
Well, it seems like the resizing rules kind of create a picture where there is U0 and U1.
Yes.
So we consider NAT bool empty and the point to be in U0. But one can ask very difficult questions. For example, suppose I consider the empty type. Should actually have different empty types in different universes. Having the induction principle for a type in a given universe only for families over this universe. Or should I have the induction principle like if you think about empty type as a product of all types, which was one of the kind of non-inductive definitions, then you can think it's a product of all types in which universe. But we don't have this so we don't go into this issue. So the empty unit booleans and NAT are in U0, and then H probe is in U1.
So the Benedikt reals also are in U1.
So the reals are in U1 because they involve subsets, and subsets are functions to H probe. So subsets of any set of a set from U0, subsets live in U1, but subsets of a set in UN live in UN other than U0.
Danny?
In your work on formalizing topology and things like that, how much were you following existing proofs were you following existing proofs in Bourbaki or making up the proofs, new proofs, or?
It depends on which notions, because as I said before, in Bourbaki there are things which are in classical logic, and then I had to read down some proofs, but for all I tried to formalize yet, it was okay. I could do it in the balance.
Do you have a sense for what proportion was newly constructivized versus?
I don't know.
Okay. And how much were you using tactics versus? How much were you using tactics versus writing proofs, sort of step by step?
I used to do it step by step.
Cool. Thanks.
Well, thanks, Benedikt.